and more interesting. Yeah, got it. So let's dive in and see what we can what I can show you here today. And actually, so a little bit about me. I'm a consulting engineer. I work for Bryan Research and Engineering. It's a company that is in Texas. Maybe the camera like this. Yeah. So it's in Texas, and we have several offices. One of our offices is in Brno, in Czech Republic, where we are taking care of our customers in Europe. And there's also offices in Dubai, and so that's like Middle Eastern office for Africa, and there's office in Singapore for Asia. So let's dive into it. So when we look at the CO2 capture, one of the most common CO2 capture is for natural gas. So when you have a reservoir and you getting the natural gas out of the reservoir, it sometimes contains various amount of CO2. I saw that in Brazil there are reservoirs with CO2 content above 50%, but usually the content is much lower. So between several persons, could be about 2%, could be about 10%, depends on the reservoir. Once you're gonna obtain natural gas with such a higher content or higher content that you see here of CO2, so you need to decrease the content because for pipeline gas, it's usually about 2 more%. For LNG, it could be 50 ppm. And if you have a 50 ppm, that's kind of hard to, you don't mine gas like that. So if you're working with LNG, then you need to have a carbon capture unit for getting your CO2 out of your natural gas. Now we can use different kind of technologies for that. One of them could be chemical solvents like amines, like ADA. We're gonna look at them in the future, like in a moment. And there's also physical solvents. They are not that common. I didn't see that much processes on chemical solvents or physical solvents, but they are also it's one of the options. Then there's membrane processes and cryogenic fractionation. But today I'm going to talk just about chemical solvents. I'm going to explain you in a while why I choose just the chemical solvents, because they're the most common one. The membrane processes, however, are something what I heard about. It's something what being used, for example, with a higher concentration of CO2. So that's something like if you have a concentration, let's say about 50% of your natural gas that is coming out of the reservoir would have CO2 inside, then you would like to use a membrane process. Okay. Here I have some industry application, some sources of CO2. I have some concentration per person, then I have the pressure in atmosphere, and then I have partial pressure. So as you can see, it's made up of 2 columns on the left. So I have a direct air capture. You can see that the CO2 partial pressure is quite of a low, right? So it's about 0.004%. It's a partial pressure of CO2. And since you have such a low pressure, the force, which you need to have in order to capture it from it, is very low. And since you have such a low partial pressure, since you have such a low force, it's very hard and very expensive to capture it. That's why we don't see that much direct CO2 capture right now. I think there is one in Iceland, but this is a very unique process. The other category would be summarizing all these processes like gas turbine, natural gas fired boiler, oil fired boiler, blast furnace from steel production and cement production. And this is something what you can see the partial pressures are varying, but they are quite of a similar, it is a similar grade, a similar amount of CO2 that is inside. As you can see, most of them are at atmospheric pressure. As you can see, the CO2 concentration varies, but what is important is look at the CO2 partial pressure. And you can see the CO2 partial pressure is between 0.03 to 0.2 to 0.6, but it's still kind of a low partial pressure. So once again, the force will be quite of a small in order to capture the CO2 out of these applications. Another cool thing would be hydrogen production. The hydrogen production is, it's, as you can see, the CO2 is, let's say, similar to cement production, or it could be similar to coal-fired boiler. But what you need to look at is the pressure. You can see the pressure is about 22 to 27 atmospheres. It could be even higher. But this is a pressure which finally allows us to CO2 have a kind of a higher partial pressure. So there's enough force to actually capture the CO2 much easily from the bulk stream. And then the last one would be ethanol fermentation, where you can very concentrated CO2 at very low pressure, but still, if it's concentrated, you can basically just clean it up and get yourself a very nice CO2 with a high purity. All right. Now I have this kind of a graph for you guys, and this is you can see it's in PSIs. That's the pressure per square inch. It's in per unit, so I convert it to bars. So that's why I have all over the place the 69s, because 1,000 PSIs is 69 bar. And usually when we, as you can see in the previous tab, you can see that we are usually working around this pressure. So it's in logarithmic scale. You can see we're starting about, let's say, 3 bar from the, and I was talking about the pressure, the partial pressure of CO2. This is for H2S and CO2, but we can just apply it for CO2. This is where you're going to get yourself with CO2 from hydrogen production. And what you try to get is you try to get it to very low concentrations like here. So you want to try to get yourself, let's say, to partial pressure about 0.069 or 0.0069 bar, even lower. So you try to get yourself to these concentrations. And as you can see, there are different surfaces, or different on this tab or this graph, you can see different surfaces. So you can see that we will be usually working with amines or hybrid solvents. So if you have a CO2 partial pressure, which is really high, then you can start to think about using, let's say, physical solvents, or high loading of DEA, which is one of the amines, or you can use about, let's say, activated hot potassium. But you can see it, usually we will be working in this area, and therefore the amines are actually the most common one for CO2 capture right now in industry. Now, what are the amines, right? Like what I'm talking about, it's actually alkanol amine. So it's an amine with at least one alcohol substituent. I guess you guys had some chemistry, and so you know like how these structures look like. And what I want to empathize here is that you can see that the molecule have basically 2 substituents, and one of them is going to be the amine, and the second of them is going to be the OH, the alcohol substituent. So the amine is one, this interacts with acid gases, so it's the one who's going to be absorbing or chemical bonding the CO2. And the OH is there for higher solubility, because we're not going to be using pure amine, but we're going to be using mixture of amine with water. So there are amine solvents, and there are different types of them. You can have a primary, secondary, or tertiary amine. As you can see, the most aggressive would be the primary one. The less aggressive would going to be secondary, and the least aggressive is going to be tertiary amine. Also, the solubility with the water also varies, but depends also on the substituent of OH, the alcohol groups. Now we look at some reaction with amines, and this is going to give you some better understanding like what's happening with CO2 capture. So when we look at this, it's like there's several chemical reactions. The first one of them is basically creating carbonic acid. And as you might know, this reaction is very slow. And if we'd be just capturing like this, the CO2, we wouldn't be able to capture it, because it would require incredibly high column, and it's basically, this is impossible. So therefore we're using the amines. And so the first one is slow, but the second one, for example, is the fast reaction. So that means like that the CO2 will react, because you can see here it is primary amine with primary amine. And as you can see, the CO2 will actually bound to the atom of the amine, or the alcohol amine. So that's what the nitrogen atom does here. So it releases the hydrogen, and in order to release the hydrogen, it will actually use it to create basically the bondage with CO2, and this is how they chemically bond together. You can also then use the other reaction that when, of course, some of the carbonic acid will be formed, and the acid will also bond with the amine. And also this is the fast reaction, but this one is limiting the third slope, this third reaction. So what you're going to see mostly will be this reaction. Now there's a third reaction, and that's because we are working with a lower pH values. It's going to be at lower pH, so you can see that the hydrogen atom will bond also, like join the amine, and it will create the activated form. This reaction is also fast. Now, with tertiary amines, the story is a little bit different, because we once again have the first reaction, which is slow, but we don't have any hydrogen atom on our tertiary amine, right? There's just 3 substituents, and there's no hydrogen atom. So this atom, this molecule needs to be activated with the H+ in order to be ready to, if I go back, to actually, we need to get ourselves to this kind of molecule, this kind of activated molecule that is able to capture the CO2. Now I'm going to show you some of the mostly used amines, of alkaline amines. One of them is monoethanol amine, this MEA. It's a very simple structure. It's bonding CO2 very easily, but it's also there's a trade-off, because if it's bonding CO2 very easily, it's also not able to just release the CO2 also easily. And this process, it's a loop. So when you have an absorption column and you have a desorption column. So in the absorption column, we want it to bond very easy. If it's bound very easily, that's very nice. But then the desorption is going to be hard, and therefore we're going to need more energy for breaking this bond again. Another one is diglycolamine, DGA, or diethylamine, DEA. And then we have some tertiary amine, for example, like MDEA, which is very commonly used, and also DPAM as a isopropyl amine, propanol amine. All right. So this was just to show you how these molecules look like, because when I'm going to be showing them to you in Promax, you just gonna see the MDEA. So I just want to give you some kind of an overview how these molecules look like. Now there's more possibility, and you don't need to always use just the one solvent or the amine, ethanol amine, but you can actually use blends of them, and that's actually very common in industrial practice. So for example, with the MDEA, since it's tertiary amine and it's slowly reacting with the CO2, we can use it as a mixture of piperazine with MDEA and of course with water, and it will help to pick up the CO2. And the way it works, this is basically like a 2 amines in one, and this one will very fastly react with the CO2, and then it will hand it over to and help to protonate. It will create protons, which will be then able to be used for will activate the MDEA, which will not activate itself without piperazine. As you can see here on the graph, there is the H2S and the CO2, but if we are working with CO2 capture, there will be basically no H2S. So therefore, you can stop thinking about there's the blue line, but there will be only the green one. But if you have, let's say, natural gas that compose H2S and CO2, and you want to remove both of them at the same time, you can see there will be some trade-offs, because once you're going to use, and this is piperazine weight percent, once you're going to be, let's say, more than 2% of piperazine, then it will actually break, and it will stop picking up your H2S, and it will actually picking up CO2, but it will be a problematic And so you need to find some kind of a point where where is the best pickup for both of these. And that very much depends on your specifications. Now let's look at some basic operating parameters. So the amine strength, it's basically the concentration. It's usually measured in weight %, and it's maintained by periodical additions of amine in actual operation. So it means that your amine actually will be, it's a loop, but your amine will be, you will be losing some of your amine through your regenerator and through your absorber. Therefore, you need to all the time add some amine to keep your flow rate as a constant. In real industry practice, they don't adding some amine all the time. They just amine it periodically. So it means, like, let's say every week or every month, depends on the used amine. It depends how volatile is that. There's one more thing. It's going to be amine loading. So the amine loading is basically how much moles of CO2 or how much of H2S. Let's say we're gonna be using for CO2 capture just CO2 for moles of amine in solution. So, and there is some maximum loadings, and there's few loadings that are also connected with that. So one of them is the rich loading. So as I said, it's a loop. So you have gonna have a rich loading, and the rich loading is gonna be for the absorber. So how much CO2 you can absorb to the lean amine. And then you are going to have a lean loading, and that's going to be connected with the amine that is coming out of your regenerator and is going to back to the absorber. I'm going to show you some examples in a few moments. All right, so it's Promax time. So I'm going to open up some Promax files. I'm going to show you how does it work. So we're going to start with carbon capture from steam methane reforming. So this one will be, I'm not gonna start just with CO2 capture itself, but I'm gonna first give you some overview of the process, so you can see how does it work, and you can see like where the CO2 is even coming from. Okay, so we can start on this flow sheet, and I'm gonna just show you a few things in here. So this is a Promax, right? Promax is a steady state simulation software that is mainly used in the industry by people that are modeling carbon capture and modeling amine gas sweetening. So it's basically for acid gas removal, but it can do also much more. We can very accurately model hydrocarbons or many different applications, but we are not here to cover all the applications. We are here just with carbon capture. So let's dive into it. So we have an air that is mixed with a fuel gas. We're going to burn it in a burner, and so that's going to create a flue gas. And this is basically the heat. It's going to create the heat that we need for our reformer. And what is on a reformer? It's going to be steam mixed with natural gas. So we're going to mix the steam with natural gas, and this is basically the process. It's called steam methane reforming. And what's happening in our reformer is basically these two first reactions. So we're trying to mix we try to react the methane with water to create a CO and some hydrogen, and also then the methane with CO2 to create some CO and hydrogen. And then there is the reaction which we call water gas shift reaction. So there is a CO reacting with water in order to create once again hydrogen. So the point of this, the goal of this process is to create a hydrogen. Now this is the flue gas that's coming through. It's just basically it's creating the heat for the reaction that is necessary. And as you can see, there's a reactor shell. So you can see that we have a heat exchanger that is connected to our reformer. So this is the reactor, and this is the heat exchanger. So it's transferred the heat from the flue gas to the reformer. And then there is another heat exchanger as a preheat, and then there's a steam generator, and this is basically mostly CO2 with some nitrogen. I can click on the stream and show you what is inside. So if you look at the composition, you can see it's basically mostly CO, CO2, some water, and nitrogen and oxygen. So that's basically our flue gas. As you can see here, I've written here it's going to be to CO2 capture MEA unit. So if we would like to make this process like whole green, then we need to even capture the CO2 that is coming out of our reactor, out of our flue gas. So here we have the preheats, and when it's preheated, it's go to the reformer. So that's the mixture of the steam with natural gas. In the reformer, if I click on that, it's going to be just a simple Gibbs minimization reactor with some pressure drop and some bypass fraction. But I would like to look at here at streams to give you a better view on what's happening inside. I'm going to look at composition, and now you can take a better look what's happening in here. So you can see that the methane is actually decreasing, and that makes sense, right? Because the methane is reacting. Then there should be water. Water is also decreasing, right? That makes perfect sense. And then there will be some CO and CO2 that will be formed. So it also makes sense that we are creating CO and CO2. And what we want to create is basically the hydrogen. So the hydrogen is created in here. You can see there are some ethane and propane. All of them basically reacts in a very similar way as a methane. So basically, you're not going to work with the pure methane, but you can have some ethane and propane, and even maybe some higher hydrocarbons that are going to be reacting. Now, you can see that some ammonia is created too, because we have some nitrogen inside. So this is basically some side reactions are also happening inside the reactor. When we react in the first reactor and we create about 40% of the stream will contain about 40% of the hydrogen, then we will go to a second reactor, which is we're going to be mainly this reaction, which is the water gas shift reaction. So once again, we have some pre-cooler, so we're going to create some steam in here, and then we will have the water shift reactor. In streams, if you look at the composition, once again, you're going to see that basically nothing happens with methane, nothing happens with ethane or propane, so nothing happening with hydrocarbons in here. The only thing what's happening here is the CO, the carbon monoxide, is converted to CO2, and also the water is being reduced because we are creating the hydrogen in here. So we need to cool this one. As you can see, it's happening at 200 degrees Celsius. And it's because this reaction is preferable at lower temperature. Now, we once again need to cool it a bit to about, cool it actually a lot to 49 degrees Celsius. So it can be more than about 50 degrees Celsius, but because otherwise, in downstream from this process, we need to have it at temperature that is suitable for absorption. If you would have it above the 100 degrees Celsius, or even more, depends of course on the pressure, your water could boil off. So therefore you need to have a lower temperature. And also the absorption is process that generates heat. So you need to be sure that even for the generation of the heat, your CO2 will not break up through and will not actually be released in the absorber. That's something which you don't want to have. As you can see, the byproduct here is some sour water. So that's also going to be created. Okay, so then we go to the last flow sheet in here, and there's going to be MDA piperazine. So right now we're using MDA with piperazine, and this is actually where all the CO2 capture happens. So we have our hydrogen. I'm going to click on this stream just to show you. So it's about 49 degrees Celsius. It's about 26 bar gauge, which is about, let's say, 27 atmospheres. And the flow rate is about 120 cubic meters per hour. And if you look at the composition, it's mostly hydrogen. It's about 70%. And there's some CO2, some methane, some ethane, propane, other hydrocarbons. But mainly we try to clean this hydrogen from the CO2. That's what we try to achieve in this unit, in this process. So this stream will come to the absorber, and you might ask, like, okay, what's coming from the other side? So if I look at the other side, the composition is going to be mostly MDA, and let me show you this in mass fraction. So it's going to be 5% piperazine. So you can see that, as I showed you previously on the graph was showing you that you should be using, let's say, about 2% piperazine. But that was for the case with H2S. Since there's no H2S, there is less limitation for using more piperazine. So you can use about 5% piperazine, and that's totally fine because it's just carbon capture. And MDA also connected with piperazine, it's about 45%. So so this is helping so we use just a little bit of piperazine to activate the MDA, and then the MDA do the work. Now, if I look at, I guess I can show, yeah, there's a water. So the rest of it is water. So mainly what is this is MDA with piperazine and some water. You can see some CO2 is still in here. And this is something what I talk about when I talk about lean loading. So when you have lean loading, there will be still some CO2 inside the, will remain in our mixture. I'm going to show you in a while what's going to be the CO2 concentration in the rich amine. So this is lean amine. So we have a lean amine coming from the up. We have the sour gas, sour natural gas, sour hydrogen with some hydrocarbons inside, and we go to the absorber. Now we have about 20 stages, but we actually model this one as the mass and heat transfer. As you can see, there's some weird stuff in here, right? This T-sweet absorber stripper. What is that, right? This one is oh, sorry. Nope. This one is actually when we started this company, it was about 40 or 50 years ago. And we actually came up with the T-sweet, which was the name of the old product. And there was a simulator focusing only on the CO2 capture and H2S capture. But since then we added more and more different kind of unit operations in Promax, and therefore we used to use this as our mass and heat transfer column type. So we left the legacy in here with the T-sweet because that was the old software. But right now it's Promax because it's do much more than just sour water. Amine gas sweetening and CO2 capture and H2S capture. So what is hidden in this T-sweet absorber stripper is actually the kinetics. So this whole column, this absorber, is not just something what is it's not a physical absorption. As I showed you before, this one is actually a reactive column. So on every stage, there's going to be a reaction between CO2 and the amines, and that will be creating the bond. So it's very user friendly because you can just specify here one thing and that's it. That's all you need to do. In terms of stages, you can see that there's some pressure drop. You can see how the pressure drop is going, how it's changing through the column. You can also see some temperatures, and you can see, I can show you it on a plot. So you can see there is some kind of a bulk in here. And this bulk is because the capture of the CO2 capture is actually, the CO2 is dissolving and it's reacting. And because it's reacting with it, it's generating heat. So it's heat because of the absorption and because of the reaction. Because of that, we're going to create some heat. And as you can see, so that's why we have some kind of this temperature profile in here. So most of the CO2 will be captured here. And as we go up to the column, the less and less CO2 will be captured through. Let me show you some more things in here. I'm going to show you a little bit about hardware of this column. So as you can see, diameter is about 3 meters. So it's kind of a reasonable diameter. You can see the diameter is changing right through. That's because we set the fraction flooding to be 70%. You can actually set, let's say, the diameter 3.2 meters and then convert it, and it will calculate the actual fraction flooding. But this is the way how you can, when you basically, you would probably start with the ideal stages, and then you, let's say, start to think about, okay, so I'm going to have a trace in there. So then you start to think about, okay, what will my trace look like, and how should I specify them? And for that, you need to click here and just specify what kind of trace we're talking about. It's going to be sieves, what is going to be the trace spacing. So that's the space between each and every tray. What's going to be the fraction flooding area? What's going to be the weir height? So there is all these specifications that need to be set in here. And you can also, of course, you can change all of them and make it the way that you want to design your column, and you can play with these specifications in order to get the best results. So you can see here it's 20 stages, but because of the trace spacing, it's 0.6 meters. The actual total height is 12 meters. So that's not that high column. And as you can see, the CO2 capture, the CO2 recovery, it's 97.75%. So that means the 97.75% of CO2 will be captured in this absorber. So that's pretty nice, pretty good number. It's pretty nice. And we can move a little bit forward and look downstream the process, what's going to happen with the CO2 that has been captured into the amine. So if you look at the rich amine, we can look at the composition and see the mass fraction in here. So you can see it's, once again, piperazine with MDA, but you can see there's about 9% of mass fraction of the CO2. There's some water and also some hydrocarbons that have been captured. And I want to show you one thing here. Okay, I want to show you the analysis. I want to solve it. And you can see here, as I've been talking about loading, you can see this is the total acid gas loading, or just the CO2 loading. So that's mean how much moles of CO2 I captured for mole of amine. And this is very useful, handy tool, but engineers usually do and usually try to work with. It's something what you can't really see in a plant, but it's very useful for you because it helps you to operate your plant. Now, this rich amine is coming to the flash tank, and you might ask, like, why is there a flash tank? Why it's not going straight to the originator? So as you saw before, there are some hydrocarbons inside, and they've been captured in there. And we don't really want these hydrocarbons to be lost into CO2 in like the final product. It's going to be mostly CO2. So we try to flush it here and reduce the pressure. When we reduce the pressure, so we're coming from about 26 bar gauge to about 4.1 bar gauge. So when we reduce the pressure in this flash tank, most of the hydrocarbons will actually evaporate here, and that's how we reduce. So it's going to be mostly CO2 and some water, but most of these hydrocarbons will actually evaporate here, so they will not get themselves downstream to the process. Then there's this lean and rich heat exchanger, and that's basically a very important part for the recuperation of the energy, recuperation of the heat, because you want to preheat your feed to the regenerator, so you don't need that much heat in your reboiler. So when it's come through the lead and heat exchanger, it will get itself to the regenerator. And if I click on this one, this will be probably modeled as ideal stages, because there is not much to, the hardest engineering part is in the absorber. The regenerator is usually easier to converge in ideal stages, and you can actually put it in the mass and heat transfer, but it usually takes forever to solve it. No, I'm just joking, guys. But I mean, you can usually use idle stages, and the rate between idle stages and mass and heat transfer is basically you have to use 2 mass and heat transfer stages for 1 idle stage. Then if you look at the stages, you can see right here that we specified our pressure to be 1.48 bar gauge. Sorry, I'm just going to move it a bit. So you can see here we were coming from 3.89. So we're going to flash it and reduce the pressure. I'm going to close this one. So reduce the pressure. And we try to get here, what we try to do in the regenerator, we're just trying to get rid of the CO2. So it will break from the MDA and from the piperazine, and it will actually be used somewhere else, or we can, then there's a question what you want to do with the CO2. Because once you get it out, then there's possibilities what to do with it. Usually you can vent it to the atmosphere, but since we are talking about CO2 capture and CO2 storage, you can actually store this CO2. And I'm going to show you how to do it just in a minute. So this is the regenerator. We're using here a reboiler. So we're going to reboil all the CO2 out of it, and we're going to get ourselves to our lean amine. Now, as I showed you here, the rich amine, the loading of the rich amine was about 0.54. Now the lean amine is 0.2, and that's something what I've specified in my regenerator. Of course, the lean loading or the lean amine, the loading in the lean amine very much depends on how much energy I want to put in. So it means like I can have a leaner amine, and that means I can have more capacity for absorption in here. But since I'm already at CO2 recovery 97.75%, I can easily leave it like this and not be boiling more of the CO2. Now there is a lot of trade-offs in here. For example, you can use a smaller column and use, let's say, lower lean loading, or the opposite way. And there's a lot of trade-offs in here. So that's, when you designing this kind of a plant, or even if you're operating on this kind of a plant, you need to be sure that what is it you try to achieve. Always you need to have some specifications, and then you try to achieve like, okay, can I reduce, let's say, the flow of my amine? So that means I'm going to have less amine, but what's going to be my, let's say, fraction flooding, right? Or if I'm going to, let's say, use let's say less concentrated amine, how it's going to affect the reboiler duty. So there are a lot of trade-offs in here. So I end up with my lean amine that is coming from my lean and rich heat exchanger. We're going to the recycle, because this is basically a loop. And from the recycle, there's a makeup block. As I told you before, we're going to be losing some of the amine and water in our absorber. So the outlet stream of our absorber, and we're going to be losing some amine in here too. Once you're gonna make it up, you have to pressurize it back to the pressure that is coming, the similar pressure that is that your stream is coming in. So you need to pressurize it again and then cool it, because you will not be able to cool it enough with your lean and rich heat exchanger. So there will be probably some trim cooler. It could be some air cooler that is cooling it to temperature that is usually about 5 degrees above or around the temperature of the inlet stream. If you're not going to cool it enough, then it wouldn't be working, because it would be still hot and it would not be able to absorb the CO2, because it's absorption column, and as I said before, the temperature, the heat of the reaction, the heat of the absorption would basically lead that the CO2 will come out of your absorber, and it would not absorb inside the amine. So this is the loop. This is the loop of the amine. So it's coming from the recycle gas. It's coming from the makeup block, circulation pump, trim cooler, through the absorption column to the rich amine. We flash some hydrocarbons in here. Then the lean and rich heat exchanger, back to the regenerator. We boil off the CO2, and then it's going back into the loop. All right. Now let's look at some CO2 compression. And so you can vent the CO2. That's the most simple way how to deal with it. But if we are looking forward to actually reduce the carbon footprint, there are several ways what to do with CO2. Of course, depends on how much CO2 you have or how much CO2 you're producing. You can produce urea, for example, with ammonia. That's one of the ways. You can produce, for example, sodium bicarbonate. That's also a possibility. Or you can actually use the CO2. And since you guys are in Baku, right?
Yes.
So you have some reservoirs in there, and you're drilling oil, so you can actually use it for enhanced oil recovery. And that's something what they've been studying and using in Texas. I believe there is one of these units in there built for our CO2 that is used for enhanced oil recovery. And for that, you basically need to pressurize your CO2. And in Promax, you can do it very simply. So you have an acid gas, and the acid gas will be, and if we look at the composition, okay, so you can see there's basically most of the CO2 and with some of the water. And you start at about 49 degrees Celsius and about 2.4 bar gauge. And you can see there's a 17,000 cubic meters, 17,700 cubic meters per hour. And then you have a series of compressors. And all these compressors will, in every stage, they will heat, because the compression it will be heating the acid gas. And at some point, it can damage your compressor. So therefore, you need to be aware, like how much it's going to heat. And I have some Excel here, some embedded Excel. Okay. This is the temperature, as you can see here. This is the temperature that is that could lead to damage of the compressor. So we try to move below it. Then there is this hydrate curve. So the hydrates can form actually with the CO2 and water. And then there is this liquid curve. So what we're trying to do here is we try to, this is our operation curve. So we try to, put this operation curve in between those two and squeeze it inside. So if I go back to the model, your acid gas will go to the first compressor. And if I click on compressor, it's going to be very easy, because you're going to just specify the polytrophic efficiency, or you can use performance curves. So let's say you know your compressor, your vendor going to give you the curves, so you don't need to use a single property, single polytrophic efficiency, but you can actually put here some curves and use it. And then there's some compression ratio, and this compression ratio will be same for all the compressors. You can actually use some specifiers and solvers for that. And that will give you, it will in every, so you will, all the time you will compress it a bit, and some water, when you're compressing the CO2, the water will actually liquefy and drop out. And that's why I have all these KO drums in here. So once again, all the time there will be some water coming out, and the rest of the CO2 will actually come to another compressor. What's also happening in this KO drum is that we need to cool it, because otherwise we would have it at the temperature coming out of the compressor. So what we're gonna do here, we're gonna cool it, and we're going to remove the water. So that's why we all the time at about 49 degrees Celsius. So we come to, so from the first compression, we go from 2.4 bar gauge to 6. Then from 6.6, we go to 16. From 16, we go to 37. You need to be sure right now, just like when you think about it, the compression ratio is basically telling me that how much I can get from one to another. So I'm basically multiplying this pressure by the compression ratio. And if I look at the duty, You can see the energy here is about 658 kilowatts. And the second one is going to be very similar. So even though you're moving from like a very low pressure to higher pressure, it's all the time going to be almost the same power. Here you can see the total compression, so it's going to be 4.34 megawatts. And then once you get yourself to target pressure, which in this case was 84 bar gauge, then you need to transport it through the pipeline. So that's why we have this pipeline block in here. And if I look at the pipeline, you see it's 1 mile pipe. There's no inclination angle. It's about 80 schedule, 5 inches pipe. You can see there's some heat transfer in here. We specify here as the ambient temperature to be 21 degrees Celsius. So it will calculate the overall transfer coefficient, inside film coefficient, all these kind of things. You can see it's a buried pipe, so that has actually a huge impact on the heat transfer. And that'll be about it. And then, so this one is the horizontal pipe. This one is vertical pipe. And this is basically the injection line. So this is the pipe that is coming to the reservoir. And if I click on this one, you will see that it will be a bit different. You can see there's more segments in here because we try because it will be changing much more since it's going down. It's increasing basically the pressure. And what you can see here in heat transfer, we actually used here a buried wellbore, and that is because it's the pipe that is going to the reservoir, and there is very important to know what is going to be the floating time, because it has impact on the heat transfer between the pipe and between the surroundings. So it will be, if you can, okay, let's look at this one. You can see the temperature in here is 41 degrees Celsius, but once it's flowing several days, the surroundings around it is going to heat, and therefore the well flowing time is necessary in here. So we have 40 days. And eventually it will end up in the reservoir. It will increase pressure in your reservoir, and it will help you to drill some more oil or and put you in the right level. But honestly, I'm not the reservoir engineer, so that would be a question for some of them. I see we have some more spare time, so I'm going to show you just last thing, and it's going to be carbon capture from gas turbine with MEA. This one will be, or if you have any question, guys, just go ahead and ask me.
Okay, actually, I have one question. Actually, I have several, but let's just have one at this time. So what you have showed is actually really similar to what we chemical engineers deal. Like, it's not carbon capture storage, but generally design projects. Just like would like to ask you, like you're a consulting company, so in what cases like clients want you to incorporate carbon capture like storage to their plant? Like mostly for what production of what requires this, and also from economical part, is it efficient for them to include this?
The most, I mean, there are people that usually at this point, I heard that in Norway and UK and Netherlands, all these 3 countries are thinking about using this. Some of them are doing studies. I believe in Norway, they already built some CO2 capture, the facility for that. But it's kind of from economic point of view, if you think about it, then there are different ways looking at it. So if you look, and if I go back in here in my presentation, so if you're working with hydrogen production, the CO2 is necessary because you actually need to get yourself to, you need to clean the hydrogen from the CO2. So you will actually need to use CO2 in there, CO2 capture in there, in order to get yourself to the hydrogen. And then what you're going to do with the CO2 is basically the question of what you're going to do is basically the question, okay, so I'm going to need some compressors. That's going to be something what might be expensive. And then you need to ask yourself, okay, so I'm going to be putting in the reservoir. Is it going to increase my production? Then it might be something what you start to think about. Otherwise, if you working in a project, let's say when you have CO2 from, let's say the gas turbine, then you will end up with, I've been talking about the column that was 3 meters in diameter and 12 meters high. If you're going to have, for hydrogen production, if you're going to have a gas turbine and you want to capture the CO2 from the gas turbine, then you will probably need about 8 meters column in the diameter, and it's going to be, let's say, about 20 meters high. And because you're working with a very low pressure in here, you can't use just trays because they would have a very high pressure drop. So then you start to need to think about packing, and that can get really expensive. So that's something what will be actually very costly. So currently the hydrogen production and the CO2 capture from hydrogen production would be something what I think is the most economically viable option. But also I heard about some coal-fired boilers in Texas. They built this huge carbon capture plant for that, and it was running for some time. And then because the price of oil was kind of low, they stopped it. I don't know if they open it up again, but that's something what they've been using in there, and it was quite of a expensive. If you want to know more about like the economical perspective, I believe we have an article for that on our website, and I can show you the article, or I can send you the link if you want.
Yeah. So if there is no material left, and there is no questions from our participants, in any ways, if there will be, if they will contact us from your permission, I would share it with you. And thank you so much. That was indeed very informative and very useful, I would say, for process engineers especially. Thank you so much, webinar. Thank you so much.
It was a pleasure. Thank you guys for having me.
Bye-bye.
Bye.